there's not much to say there. Good, I do say vector space homomorphisms there. Of course, if you've got a isomorphism, then it's bijective. So then you've got the notion of the inverse function, because any bijective function has an inverse function. And there is something to prove in this exercise, is that that inverse function is actually linear, is a linear transformation. So satisfies the, preserves the vector space operations. So something to do. It's in a tutorial. Next, in the recording, we talked about some basic properties. They're basic, so I'll skim through. We had an example in the recording of rotating a point around by alpha radians, whatever, counterclockwise in this way. Clockwise, counterclockwise. I should have said counterclockwise there by the looks of the picture. But anyway, you saw that in the recording. An important example, because we'll be using this a lot, is formal differentiation of polynomials. But here we can be working over any old field whatsoever. So it's not differentiation with gradients and all that kind of stuff. But it's just got the rule that you know and love for differentiating polynomials. So the derivative is, well, this thing here. We proved, for example, just be careful. When we're working over f5, this 5 is not 0. This 5 is still 5. The exponents in the x's, the x to the power of 5, that's still x to the power of 5. That's linearly independent from x to the power of 4, x to the power of 3, and so on and so forth. But when I differentiate it, that 5 comes down and becomes something in the field. And what it means in the field is 1 plus 1 plus 1 plus 1 plus 1, which is 0 in f5. So that term will actually die. The 2 will come down and form a 6 in front of the x, but 6 is 1 in f5. So anyway, the derivative, when you're working over a more exotic field, the formal derivative might look a bit different, but it's still given, it is this rule up here. And we proved in the recording that this is actually a linear transformation, as you already know. I mean, the rules of differentiation, they're linear. Yeah, so 0 in polynomials, 0 times x is 0. Yeah. 0 times, yeah. How come fx and gx are the same power? They're not, because here I'm saying take n to be the maximum of the 2 degrees of the polynomials. So f of x might have been 58 degree, g of x might have been 104 degree, then n would be 104. And all I'm doing in the proof of that is that I just want to be able to write sum up to n. And I take n to be the biggest of the 2 degrees, then I can just write them all sum up to n. But in the f of x, which had lower degree, all of those ai's past 52 or whatever I said, the degree of f of x, they're all 0. 0x to the power of 53, 0x to the power of 54, and so on and so forth. Anyway. It's just because I don't want to write sums going forever, because they don't. I mean, these polynomials both end somewhere, and I want to cap it off. All right? Good, I'll keep going through. So, yeah, for people who have just come in, we're after, and people on the recording, we're just going over yesterday's lecture super quickly. A key example that we'll be talking about more today, and if we don't get through everything today, we'll just maybe do 10 minutes in the practice class, so it's not too big a rush. Key example I want to make sure everyone understands is that if we have a matrix, an m by n matrix with entries in the field f, then this function here that takes a vector v in fn, I have to look at my matrix there, what vector makes sense when I put it onto the A there? This is m by n, this has to be n by 1, so it's in fn, and then this becomes an m by 1 vector, like a matrix. So that's something in Fm. So just by the way, matrix, because this is just matrix multiplication, all the associativity and everything of matrix multiplication tells us that we've got a linear transformation here. And in a way, all linear transformations on finite dimensional vector spaces are going to look like this in a certain sense. I mean, of course, this is our concrete n-dimensional F vector space. This is our concrete one where we're writing everything as vectors. But there's other n-dimensional F vector spaces, namely polynomials of degree less than or equal to n minus 1 with coefficients in F. That's an n-dimensional polynomial. But as soon as I fix a basis of that, might as well pick 1, x, x squared, x cubed, up to x to the n minus 1. Once I pick a basis, I can represent elements of that n-dimensional polynomial vector space as now just thinking of them as vectors where I just put the coefficient of 1, coefficient of x squared into a vector. And once I do that and start thinking about my vector spaces equipped with a basis, that's the extra bit of information we have to add, really all of our n-dimensional F vector spaces are isomorphic, as we discussed a bit later in the lecture yesterday, and we'll see it today. Anyway, so this example is really a key example. Like, it's basically all examples in finite dimensions look like this in a certain sense. All right, so make sure you know. And then I discuss that. Well, first I say, so something less, I'm saying a bit less than what I was just chatting about here. This is saying if I want to take a linear transformation from this vector space to this one, so not an arbitrary n-dimensional to an arbitrary m-dimensional, but we'll get to that in a minute. They're all of this form. And to see this, first note, I guess I did this in the lecture, in the recording. But what I want to say there, oh, sorry. No, that's not where I put the proof. The proof is here. Proposition. So once we do have a linear transformation and a basis of our domain, V, then as soon as I know the values of theta on all of the basis elements, then I know the value of theta everywhere. That's what we're saying here. And that's obvious because it's a linear transformation. So once I know it on a basis, then, well, an arbitrary vector is a linear combination of those basis vectors. And by the linearity of a linear transformation, I mean, by its definition, I can take theta of a big linear combination and write it as a linear combination of theta of the basis vectors. So once I knew those theta are evaluated on the basis vectors, I know it everywhere. So that's a really important fact. So it's just immediately from the linearity. That's what blah, 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 all of that is. Up to that square, that's what I explained up to there. And that claim saying that every linear transformation from Fn to Fm, that's the way it works, n to m, is of that form. I just take this matrix where I clump together theta evaluated on E1, that's some vector in Fm, so that's going to be an m length vector. M, not length's the wrong word, but you know what I mean, m coordinates. And similarly all of these ones. So this is an m by n matrix. And then just quickly use the proposition. Well, immediately, by the way, matrix multiplication works. Theta m matrix multiplication onto the standard basis vector Ej is just this. That's what it, when you multiply a matrix onto a standard basis vector, it just grabs the jth column of the matrix in question. That's what that, just by matrix multiplication. So it grabs the jth column, which was here somewhere. And so that is theta, because it agrees on the basis. It's linear by the previous discussion on the key example. So that's what it is. All right, good. Let's just keep going, because linear transformations are so important. I don't want to risk people who haven't watched the recording, then you won't understand today. So we'll continue on. Had an example. Whatever. That's just an example of what I was talking about. Super important concepts with linear transformations, and more generally with any homomorphism between any algebraic structure, are images and kernels. Sort of weird name, kernel. I don't know where it comes from, but anyway. This is how they're defined, at least in the vector space world. So the kernel of theta, it's everything killed by theta, you often say, but by kill means mapping it to 0. Okay, everything killed by theta. And the image of theta, on the other hand, is, well, this is the, remember the subtle difference with a function. A function by definition has to have a domain and a codomain. That's really part of the definition of a function. The codomain doesn't have to equal the range, which we're calling image now, because it's the more formal word for it somehow, better word, I think. The image is the set of set of outputs that are actually, achieved. They're actually theta of v for some v. So that's some subset of the codomain. And what the proposition below, no doubt, is saying is that the kernel is a subspace of the domain, and the image is a subspace of the codomain. Okay. So they're not just subsets, they're very importantly subspaces. That's what we say here. And similarly, to say that theta is injective, there is a tiny bit of work to do to check this if and only if. Injective means if theta of x equals theta of y, then x has to equal y. But by the linearity, you can bring the y across the other side, and it's theta of x minus, theta of x minus y equals 0. So at the end of the day, you just have to work out the things which map to 0 for to know if the only thing that maps to 0 is 0, then it's injective. If other junk is mapped to 0 as well, i.e. if the kernel is bigger than 0, then it's not injective. Okay. But anyway, that's the standard way, so really emphasize that. If you want to know that theta is injective, which you often do because you might want to try to prove it's an isomorphism or something, you check that the kernel is 0. So not that the kernel's empty, it's not empty, it always has 0 in it, but that's all it's got in it. And surjective is, by definition, the image equals W. I mean, that's definition of surjective. By definition, good. A remark. What am I saying here? If A is that and B is that, then... Oh, yeah, okay, so I do want to come back to this, actually, in a minute. So if we've got a matrix and we now define the linear transformation associated to A, which is just given by matrix multiplication, then the image of A is nothing more than the column space of A. And here's the explanation that I explained a slightly different way in a practice class, but there's the explanation. So that's also worth remembering. I'd prefer to just, this might be also written image of A sometimes rather than image of theta A. Can write just image of A if you like. It might be a bit clearer to write theta of A. But it's the same, whether we're being pedantic, calling A the matrix, theta A the linear transformation. Sometimes it's sort of good to separate it in our minds. And I'd normally say image of something, but column space is this more sort of traditional, a bit more old-fashioned, I guess, when you're talking specifically about matrices. All right. So there was an example here. There's our linear transformation given by just a matrix multiplication. Find bases of the kernel and the image. So this is something you'll certainly be asked to do at various stages. I haven't written the exam or anything, so I'm not saying it's in there necessarily, but you have to know how to do this. So first of all, I sort of maybe didn't explain properly last week finding a basis for the column space. I just quickly said some stuff. So I will go over that a little bit more. Let me say here C star, and I'll jump forwards a little bit to some notes I've made for today's lecture. But anyway, first for the image, we just have to find, it's the same as the column space, so we have to find a basis of the span of the columns, and that's what they are. And quickly to jump forwards and more clearly say what the technique we should be doing there is. That's all yesterday's lecture. So here's today's lecture, but I just wanted to start with two things, but I'll jump back and forwards a little bit. So here it is what I want to say, just to say it very clearly once. So remember how to find the basis of a span. I did talk about its way with transpose. I actually meant to remove that from lecture because it's correct, but it's just a bit confusing, so what I said last time. So we don't really use that much, but anyway, it's right, so you should remember it. But this is more the, if I normally ask you to find the basis of a span, and I don't care that that basis is a subset of the span. So what I talked about the other day was explicit, the way you took transposes and did row operations. That was trying to find a basis where that basis is a subset of the vectors v1 up to vm. Now I ignore that. Okay? I just want to find a basis. An efficient technique is as follows. Make the matrix A by just sticking all the v's into columns. No transposes. So that's why I sort of wish I hadn't said it, because as soon as you've said there's one with transpose, one without, then you forget which one's which. Anyway, don't transpose stuff here for this thing. Now reduce A to row echelon form. And the problem is there, like in principle, until you think about it a bit more, the columns of once you're doing row reduction, don't seem that clear. You don't get the same column space. I mean, once you start doing row operations on a matrix, the column space will change. But the point is the column spaces are isomorphic as you make row operations. So we'll explain that a bit more later on. But for now, I'm just recalling from 1061. So reduce A to row echelon form. And so what you do is you look at the columns in your reduced row echelon form, or row echelon form. You can go reduced if you like, but you don't have to. Just row echelon form is enough. Find the columns in your row echelon form that have the pivots, those leading entries. Okay. Then the corresponding columns of your original matrix. So for example, in our row echelon form, let's say columns 1, 3, and 5 were where the leading ones were, those non-zero entries. Then columns 1, I've already forgotten what I said, whatever it was, 3 and 7 of the original matrix form a basis for the column space of A. Okay. And what's really happening there, we'll discuss it a little bit more clearly next week. We could do it now, but it just takes a bit of time. It's easier next week once we've discussed some more stuff. What's really happening is that the column space of the matrix and its row echelon form, they're both isomorphic to each other. With the isomorphism, maybe we can say quickly, it's given by multiplying by the elementary matrices that you used that did the row operations. And elementary matrices are invertible, so you're getting an isomorphism from that column space to the next column space to the next one to the next one. So, as we discussed earlier, or as we discussed later in today's lecture actually, yesterday's lecture, once you have a basis and an isomorphism, it sends a basis to a basis in the codomain, in the image. Anyway, I'll freeze that and then zoom back up. So sorry it's a bit out of order. I just want to emphasize that. So back to that example from yesterday. We're trying to find a basis for the image. So we're trying to find a basis for this span. So we do exactly what I just said. Whack the vectors into a matrix without doing any transposes or anything. Do row operations, get yourself into row echelon form. The columns that have leading entries, leading ones, if you've rescaled everything, but they're called pivots or whatever normally. These pivots here, the leading ones, that's in column 1 and 2, and therefore columns 1 and 2 over here form a basis for this span. So, sorry, I've confused, I've said something confusing also. I said earlier that last week that method where you transpose things found a basis that wasn't a subset of the original set of vectors, but it was a nice basis. It was in some kind of echelon form. This method finds a basis which is a subset of the vectors themselves. Sorry, I said something confusing 2 seconds ago. Anyway, I hope I haven't made too much of a mess of that. And I hope you remember that technique now. All right, any questions about that? All right. But actually to find the basis of the kernel, we also have to do row reduction. So we have to take A, put the 0, 0, 0s, because we're trying to solve the matrix equation AV equals 0. And we do the same thing. I mean, we've already done the row reduction. So actually it's one and the same work. To find a basis for the image and a basis for the kernel is all one and the same. Reduce the matrix down. For the image, you just read off the columns of the original matrix corresponding to these ones here. For the kernel, you remember to put your 0, 0, 0s there if you like. You don't have to do the row reduction again, of course, because it's the 0, 0, 0s stay as 0, 0, 0s. And now just solve the matrix equation over here, which we do. We've got two free variables. We go about doing junk, and we get the kernel, as usual, solving a matrix equation. And just the way that process works of reducing a matrix to row-reduced form, the two free variables will give you the dimension. I mean, it's clear in the example. These are linearly independent vectors. Why? Because they have zeros in different places. It's where the zeros are that makes them, you can't make a linear combination that is 0, except for taking 0 for both coordinates, both coefficients. All right, super important. Find a basis for image and kernel. It's just row reduction. Exercise, make sure you can do that one. The next observation we made yesterday was, about injectivity, surjectivity, about linear independence and spanning property. And this is the way it works. Theta is injective if and only if, you could say it another way, if and only if the image, these vectors here form a basis of the image. But actually all I need to say there is that these are linearly independent in W, in fact. So not a basis of the codomain, because the codomain could be huge, of course, but those vectors linearly independent, then they will be a basis for the image, because they span the image, obviously. And theta is surjective if and only if, so now we really care about the codomain when we're talking about not the image, we care about the codomain. We want the codomain to equal the range, codomain to equal the image, and so these guys have to span the entire codomain. And so theta is an isomorphism if and only if the image of a basis is a basis. That's the punchline there. Okay. So isomorphisms map bases to bases, and indeed anything that does map a basis to a basis is an isomorphism. Okay. Very important, with important, sort of not like proofs that are just straight from the definitions. There's this quite striking consequence that it basically, because isomorphism is to a certain extent the notion of being the same as vector spaces. I mean, yes, you're calling the objects in the vector space different things, but up to how they add together and scalar multiply, they're really the same. If you relabeled these ones, called them these things, like made a this bijective linear transformation between them, then they're the same vector space. Same is not the right word, but you know what I mean. As close as possible. And what the theorem is saying is that for each n, there is really up to isomorphism a unique n-dimensional F vector space for the given field F. Okay? They all look different, like Fn looks different to polynomials of degree less than or equal to n minus 1, but they're actually isomorphic, is what this theorem says. Anyway, and the proof was there using the proposition. So in particular, this is what the example I've been talking about earlier. I've shifted the n minus 1 up to n now. This guy is an n plus 1 dimensional F vector space, so it's isomorphic to this guy. Okay. And as I say here, it has very practical consequences. Because Fn is concrete, we can make calculations with matrix multiplication and all that junk. And so actually what we're going to talk about today is exploiting that idea to represent linear transformations using matrices. Later this week, actually today. And then homomorphisms. We get a whole vector space worth of homomorphisms. So we take the set, the V and the W are fixed vector spaces now, and we take the set of all linear transformations from V to W. And what the theorem down here says is if we add two linear transformations, we again get a linear transformation. If we multiply one by a scalar, we again get a linear transformation. So that set of linear transformations is actually a vector space of linear transformations. So it's this extra level of, we have V's and W's to begin with. Now the set of all linear transformations itself becomes an F vector space. We'll discuss later, I can't remember if it's today or next week. At a certain point, I mean, you can also compose. If you make this V and this V, so they're both the same, homomorphisms from V to V, then you can also compose linear transformations. So then you've got this extra structure. It'll still be an F vector space, but it also has a multiplication of vectors. So it becomes an algebra, ring, we could just say ring at this stage. But anyway, good. So we have a whole vector space of linear transformations. Oh no, I did say that in the recording, so I can't remember what was in the recording. So if I match it up so that domains equal codomains in the right way to make the composition work, then I can compose two linear transformations. Composition of linear transformations is again linear. That's something you have to check once in your life. That's what one is. If they're both injective, then the composition is injective. And if they're both surjective, then the composition is surjective. So if they're both bijective, then the composition is bijective too. So composition of isomorphisms is, again, an isomorphism. Exercise, do it. All right, now we're on to today's lecture. As I say, we'll continue a little bit into the practice class. So I wanted to just revisit two things. One of them I've already done. Another one I realised also in this week 2 lecture, I forgot the thing I said last year, but I didn't say this year, just this corollary that's just a very useful fact to have. So the proof is immediate from what we've done previously from the characterization theorem, but it's just worth emphasising this statement. I'll freeze it so I can make those things there. Just put in a nutshell, what I want to say is that if you've got an n-dimensional F vector space, so I've omitted the F, but F vector space, then any n vectors, so if you've got enough vectors that span, so any n vectors that span V will form a basis. So it means that if you've got a counting argument, so if you know the dimension in advance, then you only have to check one of linear independence or spanning. That's what we're saying. So if the vectors span, then they're also linearly independent and form a basis. Conversely, if the n vectors are linearly independent, then they're automatically a spanning set and form a basis. So once you know the dimension and you've got the right number of vectors, only one of the two conditions of being a basis is important. Anyway, and that just comes from the characterization theorem of minimal spanning sets, maximal linearly independent sets. Okay, that those concepts mean a basis, and they say these two things. All right, sorry to quickly go over that, and that's what I talked about earlier. And I've got an example. We just did an example earlier. Any questions about linear transformations? So yeah, sorry I was away yesterday, but that's the way it is. All right, so the point now, oh yeah.
How you said like those two theorems, could you say that that's true because of the implications of its Barbie trends?
Yes, you could as well. Yeah, that.
Two of them were linear
You could phrase it that way. Yep. You could phrase this I'm thinking, if you're thinking of it as a matrix, I think you'd be trying to imagine we'd have to put our V as being isomorphic to an Fn, using some stuff we talked about earlier on, and then think about the matrix whose columns are given by, and then so these vectors now become columns, and now think of the matrix with those columns, and treat this as a linear transformation from the vector space to itself. And then I think the interpretation you had would work. But there's a bit of twisting and turning to do there. I think it's better to use the characterization theorem. Yep, so what I'm saying is if you think of V is Fn, take the matrix with those columns as its columns, think of that now as a linear transformation from the vector space to itself, and then use this all of this stuff that, not here, use this stuff here. Yep. All right. There's certainly more than one way to skin a cat with linear algebra. All right. Getting back to matrix representations now, we're trying to exploit the fact that there really is only one n-dimensional vector space up to isomorphism, and that every linear transformation from an Fn to an Fm can be regarded as can be written as a matrix. So we should be able to write every linear transformation as a matrix once we realize or choose concrete isomorphisms with V to Fn, and similarly W to Fm. But that's the part that there's no canonical choice. I mean, there's infinitely many ways in a vector space where the field is infinite anyway. There'll be infinitely many different isomorphisms, in fact. Like Rn is isomorphic to itself, where you just map that standard basis vector to 3 times itself, and this one to 7 times itself, and this one to, they're all isomorphisms from Rn to Rn. So the point is now we have to add a bit of extra data. We have to take a vector space with a basis. And once we do that, we can start writing things down. Coordinatizing things, if you like, is another way of thinking of it. The matrix you get is certainly going to depend on the bases that we choose. Oh, and choosing a basis is the way we choose this isomorphism, right? Because an isomorphism, remember, is determined by where it sends a basis. So maybe it might be clearer to think of the isomorphism going back this way. I want to take an isomorphism that takes the standard basis here and gives you something. Okay? And those somethings are going to be my choice of basis over on the left-hand side. And the details work as follows. And let me now zoom to the part of the lecture that I'm at. So, as discussed, we have to fix an ordered basis. The reason ordered is because I've got a matrix with rows and columns. So not only picking the basis, but which one's the first element of the basis, which one's the second. That'll tell me which one's the first row, second row, and all that kind of stuff. So the way the notation I'm typically going to use is a capital letter, like with a vector symbol under it. But it's not a vector, it's, well, it sort of is a vector. It's a vector of vectors, but think of it just as a sequence like this, an ordered basis. So it's a basis with a choice of which one I want to call the first element of the basis, and so on and so forth. Similarly, I'll say later, I'm going to do one for W as well, but not right now. So the coordinate vector of a vector V in V with respect to this basis, so now everything's going to be with respect to the chosen basis, So we need some notation here as well. So I'm going to use little square brackets around the V and the B down the bottom, telling me that it's with respect to this basis. And it's just lambda 1 up to lambda n. So note that it's something in Fn where, what are the lambdas? The lambdas are what I get when I write V in terms of the chosen ordered basis. They were called B1 up to Bn. Okay, since it is a basis, I can write every vector as a linear combination in a unique way, and that uniquely determines this vector. So essentially what we are trying to do, the philosophy is we're trying to not think of our complicated vector space V as a complicated vector space. We're just going to keep track of coefficients in vectors like this. Okay? That's the philosophy. So we write C with the subscript B for the so-called coordinate map. This is the map that takes our vectors V, vector space V, across to Fn for the, let's call it the coordinate map. C, B of V equals this coordinate vector. Okay, so this is just explicit. So we've discussed down there what the coordinate vector is. Now we just, that assignment, taking vector to its coordinate vector, we call that a map. And no surprise, it's an isomorphism from, it's a linear transformation. That's clear. And it's also maps a basis, because this was a basis over here. It's mapping them to the standard basis. So, I mean, where does it map B1? It maps B1 to, that's lambda 1 equals 1 and everything else 0. So it maps B1 to the standard basis vector E1, B2 to E2, B3 to E3, and so on and so forth. So it maps a basis of V to a basis of Fn, and therefore is an isomorphism by what we just talked about. So CB is an isomorphism. As it maps B, the B basis, to standard basis. E1 dot 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 En of Fn. Okay? So now continuing, let's bring a linear transformation into the picture now. So what we've done so far is just coordinatizing our abstract vector space as a concrete vector space. Now we have a linear transformation as well. And fix ordered bases. Well, we already had B. So let's say V was n-dimensional. I'm assuming that we've got finite dimensional vector spaces. The same ideas are fine for infinite dimensional ones, but your matrix now becomes like an infinite array of things. But it's a bit tricky in that because we're not, the basis might not even be countable, so that means you can't really put it as a as an infinite matrix because you don't know the first, second, third, fourth elements of your basis because it's not in bijection with the natural numbers. So we're happy to finite dimensional vector spaces at this part of the course. Good. And continue with that. And let's define a function, theta twiddle now, with the twiddle up the top, from Fn to Fm via the following diagram. And so the idea, to explain what's going on, so we've got our linear transformation theta from V to W, and then we've got our concrete maps that take V, and these are isomorphisms, so I'll draw them like that. These are the ones that take us to Fn and Fm, respectively. These are these coordinate maps. This would be CA, which is a map from W to Fm, and this one was CB, which is a map from V to Fn. It was an isomorphism from there to there. And by following this diagram around, I can make a map theta twiddle from here, and the way I have to find theta twiddle is I have to go upstairs first. That's okay, I have to go backwards, but that's an isomorphism, so it's got an inverse, and then go across here, and then go back down here. But so really what it's doing, it's trying to rewrite our theta as an explicit theta on these concrete vector spaces that that completely encodes what the original theta did. Because once you tell me this theta twiddle, I can of course find out theta, because I find out theta by going boop, 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 like go around that way. Okay, so once you know theta twiddle, and the other way around as well. So to be a little bit more explicit, so that what do I mean by saying define it by the diagram? That is, theta twiddle is defined to be the coordinate vector B inverse composed with, remember how composition works, you've got to read it in function order like this, composed with theta and then composed with the coordinate map CA. And that ultimately is a map that starts in Fn and ends in Fm. Yeah. Okay. Continuing though, the point is we want to be able to now use all that. So you should think of this as coordinatization. I mean, you have this abstract vector space V. Once you pick a basis, you've got coordinates by just linear combinations when you write things as linear combinations in the basis. And now we want to ultimately write our theta. Well, we want to just write out the matrix for theta twiddle. Okay? So I think I've got a few minutes left. Yep, good. By the key example from last time. In the recording, but we explained it earlier. Every linear transformation from Fn to Fm can be represented by a matrix. So theta twiddle is indeed represented by a matrix. Which we'll denote as theta, because it's the matrix of theta with respect to these two chosen bases. And at this stage, pay attention to where the A's and B's go here. Remember when we had a matrix that was an M by N? That was a map from Fn to Fm. Sort of a bit of a backwardsness of the way you read the indices down the bottom, subscripts. Similarly here. The B is a basis for the domain, the V from earlier, and the A is a basis for the codomain, the W. Theta is a map from V to W, V to W. Just to emphasize, it's really important that once you get the notation in the right order, everything will behave like matrix multiplication with rows and columns, and it'll all be okay. If you get it the wrong way, then you're in a mess. So explicitly, what is theta of AB? It's, well, we discussed from the key example, it's meant to be the matrix of theta twiddle. And the matrix of theta twiddle is the matrix where I just take theta twiddle evaluated on the standard basis as the first column, second basis vector, standard basis vector, and the nth basis vector. And this is a matrix with m rows, n columns, and entries in the field F. Okay, but I want to unpack that now and write these theta twiddles all in terms of just the coordinate maps and theta itself, so that we don't have to talk about theta twiddle ever again. And I'll do that in the last 2 minutes. But theta twiddle of the jth basis vector is by definition none other than CA composed with theta composed with CB inverse of the standard basis vector. What does CB inverse do to the standard basis vector? Well, remember we want CB was mapping our basis B to the standard basis. So the inverse maps the standard basis back to our basis B. So that's B. And now this coordinate vector, so this is CA of theta of B, if you like. And so what that means is I have to take this vector here. So how do I compute this coordinate map? I have to take this vector, write it in the basis of AI's, and grab the coefficients and write them as a column. And that's what this will be. So in other words, this is the theta B subscript j, the 8th coordinate thing. So to summarize that, and then we're going to do heaps of examples on Thursday. If theta of B subscript j is mu1 A1 plus, so this is something in the image, so I can write it in the basis of the image, well, in the basis of W in fact, basis of the codomain. Call that star. We have theta twiddle of EJ from the calculation we just did above is exactly this vector mu1 up to mu n. So the coefficients in star give columns, give the jth columns in fact, gives jth column of theta AB. So it's going to take, we'll refresh this again, we'll come back to it, but what the point is, when we're trying to write out the matrix of a linear transformation, we take our basis, we apply theta to each element of the basis, we write that in terms of the basis over in the codomain, grab those coefficients, turn them into columns, and that's the matrix. Yeah?
Why is it N? I thought it doesn't.
Yep, that should be an M. That should certainly be an M. That's an M down there. So, literally 1 minute. This is the summary. It's what I've just said. We've got a linear transformation, fixed choices of ordered bases. The matrix with respect to those fixed choices is the matrix in here, whose jth column is given by writing theta B subscript j into the A basis. And I'll just finish this sentence, put that another way. this equals the matrix Cij, where theCij's are given by this formula. We'll come back and continue in the practice class with examples, and the practice class has lots of examples. Okay. Any quick questions? All right, good. It's a confusing topic, the matrix representations with rows and columns and stuff, but just the philosophy, remember, it's just making an abstract transformation concrete.
Oh, I'll upload that. Yep, I'll do it.
What reason why?
Yep, no worries, thanks. In today's lecture,
Why do you need to go back here?
oh yeah, because we're trying to make a map from here to here, and when I say define it by the diagram, I mean that to define this map, I go,
What are V and F?
V is, so what we started with were these two abstract vector spaces. V is dimension n, and W is dimension n, and a linear transformation between. That's theta. And then once we fix bases of V and W, we get concrete isomorphisms from V to Fn and W to Fn.
What's the F and
These are isomorphisms.
just like the basis?
But when you choose a basis, it gives you a concrete isomorphism to Fn.
Okay.
So Fn is this explicit, length vectors with n
So
components.
you convert the basis of V to Fn to the basis of W.
Well, yeah, I mean this isomorphism will map the basis here, our choice of basis, to the standard basis here.
Okay.
That's the way the CV is defined. That's the map which takes out choice of basis here and maps it to E1 up to E.
So what were we proving here?
So we're not proving anything, we're defining something. So we're defining theta twiddle, and we're defining it by this diagram. And what I mean, so it's really, if you want it as a simple, it means this. I mean, I could have just written this, but it just means to tell us what's happening.
I mean, overall, what was the proof trying to show?
The proof is there's no proof, there's no theorem today so far. It's defining the matrix of a linear transformation with respect to choices of bases.
Okay, so
The definition is the definition of the matrix representation of theta with respect to these two bases is it's the matrix of this linear transformation, theta twiddle, and that's what we. So no theorem, just the definition.
Thank you.
Yeah, I have a quick question. With the A of the I, what is that?
E.
Yeah,
Yeah. So the AI was it an A or an E?
an A. Like the E's of
The E's. The E's are the standard vectors. So E1 is 1, 0, 0, 0, 0.
What about complex though? Over the complex.
Yep, it's all fine. So no matter what the vector space is, over F, vector space F,
Yeah.
it's still the 1 of the field,
Yeah.
0, 0, 0, 0, 0.
But then how do you get complex?
Because there, the scalars are complex numbers. So you can multiply, if I was looking at C squared, C2,
sure.
then you multiply complex numbers into all of those coordinates.
Copy. Yeah,
Good,
thanks.
excellent, good one.